You've just come home from your 12-hour shift at Kamiri Labs. It's time to lay back and de-stress with some of your favorite tunes. To your dismay, you find that changing songs requires an extraordinary amount of effort. Who has time to reach over for the darn skip button every time he or she wants to move on to the next song? That's where we come in. Presenting the Lazy Man's Radio, an inexpensive and modern alternative to today's music players. Simply wave your hand in front of the sensor to trigger a skip to the next song. Our music player features all the standard capabilities of its contemporaries for a fraction of the price. Now this video is going to be a mostly technical discussion about the implementation of our project. If you want to see a demo, please refer to the demo video link featured in the project report website. Now the remote operation of music playing devices has been desirable for a pretty long time. Personal music devices like an iPod or an MP3 player have been pretty nice nowadays because they allow easy access to music. But sometimes interfacing with these devices can be unwieldy in social settings because you have to reach over for the screen and otherwise divert your attention from whatever you're focused on. Being able to change the song with a wave of your hand could be extremely convenient in social settings like parties. The features of the Lazy Man's Radio. The Lazy Man's Radio comes with pretty much all the standard capabilities that you'd expect from a music player, including an LCD screen that outputs information about the track that's being displayed, a motion detector via this PIR sensor over here. We have, as an alternative to the motion detector, the standard kind of push button that would allow you to skip to the next track if you wanted. A set of LED indicators right over here that indicate which song you're on. Note that the LCD also does this, but the LEDs are also just like another way to determine which song you're on. The shift register, which is right over here, allows us to use very few pins on GPIO pins on the MSP430 to interface with many pins on the soundboard. In some sense, it serves as a decoder device, but that will be discussed later in the presentation. And we have a soundboard that features 8 of today's most popular hits that play on this mini speaker right here. Now, we'll talk about the parts that we used to assemble our product. The first part we used was a 16:2 LCD screen. This means that there are 16 characters in one line and support for 2 lines on the screen. And we used this to display the track name for each particular song that was being played at any given point. At first we considered using a backpack, which served as a controller around this model to reduce the number of pins, but we ended up not doing so, and the reasons for that will be discussed shortly. We used an 8-bit shift register, the 74HC595, to serve as a way to reduce the number of pins of the MSP430 that the soundboard uses. It serves as a one-call decoder, and again, this will be discussed later in the presentation. As an alternative to the PIR sensor, we provide the standard radio-like functionality of a push button that allows you to press it to skip to the next song. And the soundboard here is actually the heart of the entire product because it allows us to hold up to 15 minutes of compressed audio and play it back in ways that we will also discuss shortly. Now, the main microcontroller that we used as our embedded system controller was the MSP430, mounted on the MSP430 launchpad as shown here. We use the G2553 model, which is very low cost and has low power consumption, and it's pretty easy to interface with the GPIO pins using the MSP430 variant of C. The PIR motion sensor is just an infrared sensor that detects motion within a cone of, I think, 130 degrees from its center point. It's pretty low power consumption, and its output pin, it goes high to 3 volts whenever it detects a motion and stays at that range for roughly about 5 seconds following the motion. To power our soundboard and speaker, we used a USB power supply, the same kind you would use to charge your phone on the go. And for the mini speaker, we ordered this part off of sparkfun.com to play the sounds from the soundboard in a way that everyone around in the environment could appreciate. Now this is a presentation of the schematic, and I don't want to bore you with all the details, but I want to show you like a few of the things that are pretty important in interfacing with the peripheral devices we had. Now as you can see, the MSP430 has 20 pins, but only 16 of those pins can be used for GPIO. Naturally, this brings into question, like, is this going to be a concern when it comes time to mapping pins to different functionalities of the peripheral devices? And yes, it was a concern, but notice that with the clever usage of things like the shift register and the way we ended up using the 4-bit interface for the LCD display instead of the 8-bit, we managed to save like many pins on the MSP430. I think probably like 6. And this allows us to extend our model in the future to do even more than it was originally designed to do. I'll briefly go over which components are which here. We have the MSP430, the heart of the embedded system. We have the LCD display that the user will typically interact with to see what song is playing or what artist is on. We have a PIR sensor that serves as a controller around when to cycle to the next song. And we have our soundboard here that serves as the means by which we power the speaker to play audio that we'd like to play. Now let's talk about the hardware architecture, and this is really the meat of our discussion today. So there are 3 main problems that we had to solve when dealing with our project. The first was interfacing with the soundboard. The second was interfacing with the LCD, and the third was interfacing with the motion sensor. I'm going to go over each of these in a pretty great detail to give you an idea of what kind of problems we faced and how we overcame those with solutions. So let's start by going over the soundboard. We purchased the Adafruit Audio FX soundboard because of its low cost and simplicity. The soundboard has 11 pins that can be used to play songs, and all you have to do to play a song from a certain pin is to drive the corresponding pin low. Note that if multiple pins are driven low, then the pin with the lowest number assigned to it in like the order of natural numbers will be the one that's played. However, as we discussed earlier, the MSP430 only has 16 GPIO pins. So how are we going to be able to play all the songs on the soundboard while still allowing enough pins to interface with the LCD and any other peripheral devices like the motion sensor that we had? And our solution to this was a clever design taken from our elec 326 knowledge, and we thought of using a one-cold decoder, which is a combinational logic circuit that allows you to input a certain amount of pins, input lines, and depending on the numerical value of the overall input lines when represented as a number, one of the corresponding 2 to the n output lines will be driven high. In other words, this means that we could have controlled 16 pins, 16 output pins with only 4 GPIO pins of the MSP430, which is like a great improvement, right? Because we only have to use, log base 2 of how many ever pins we want to control instead of using, all n pins. However, we had some minor fears about what this could mean for our project, especially with regards to timing issues. Say we drove 1 bit of the input to the decoder high and wanted to do so with other bits as well. The problem is, as a combinational logic device, the output is always a function of the input and never a function of the clock, which means that sometimes you'll have issues where not all values will be written to all the input lines at once, and you'll have multiple tracks start flickering before the final track has been selected. To get around this, we used a sequential logic element called a shift register, and it allows us to control 8 pins with only 3 GPIO pins. You can scale this as much as you want without increasing the number of GPIO pins if you are clever and you daisy chain your shift registers appropriately. We didn't do so for this project. We just decided that 8 pins out of the 11 we had possible would be good enough, but if you wanted to do so, it wouldn't be too hard. Let's discuss the LCD display. The LCD display was probably one of the harder parts of this project in terms of its GPIO pin requirements. So we tried using the SPI/I2C backpack, which is another component on Adafruit that allows you to communicate with the LCD using only 3 or 4 pins instead of 6 to 7. However, the support for recommended libraries with the MSP430 is pretty limited, and I tried porting the code, the drivers, to the flavor of C that the MSP430 uses, and it is pretty hard. So we decided to stick with the traditional interface for the LCD display and sacrifice those 3 or 4 extra pins because we did have some pins left over thanks to the decoder and other clever design strategies. Let's for a minute just discuss the LCD hardware interface and how to approach that as an embedded systems programmer. One of the main sets of things we'll have to discuss as an embedded system programmer is the set of pins that you'll have to deal with, right? So the first pin is the RS pin, and what that does is it gives the LCD unit knowledge of whether the incoming instruction is to be treated as a special command by the MPU, which is like a CPU except in signal processing devices, or if it's to be treated as a regular character that should be written on the screen. The RW pin signifies whether or not the instruction that is to be executed should be treated as a read or a write operation. Since we were only doing writes, we happened to ground this pin to allow us to save a pin in the GPIO because we didn't actually need to interface with this pin. We can just ground it. The E pin stands for enable and tells us, or tells the device rather, that we're going to start transferring data. And we have 2 sets of data bits 4 to 7 and data bits 0 to 3. If you're using this device in 8-bit mode, you would be channeling GPIO outputs as inputs to each of these bits. But since we were operating the device in 4-bit mode, we left DB0 to DB3 unconnected, and DB4 to DB7 were connected to GPIOs of our MSP430 to write the appropriate values. Now, the way to interface it with it as an embedded systems programmer, you could do it in one of 2 ways, right? If your life is, cut out for you, then somebody's already built a device driver or a library for you that can interface with the lowest level of operation, the registers that drive the LCD, and that's actually what we ended up doing. My roommate Kevin wrote an LCD device driver for the MSP430 last year, and we ended up just using that, which allowed us to program at a high level rather than at the lowest level of operation. If you're unlucky, then you just have to try porting the code yourself, and it's actually what we tried doing with the SPI I2C backpack, and it is pretty difficult. The next piece of hardware is the motion sensor. Now, we tried dealing with this a couple of ways. The first way was as a flight sensor, and we wanted to use a flight sensor because it would give us accurate readings of detected objects in the vicinity. Based on some of the images on the actual object's web page, it seemed like the compatibility with I2C would allow us to get a good, precise reading of where the object lay relative to the sensor. However, it is really difficult to implement the I2C, and it was almost an insurmountable challenge after some point. So we ended up switching to another device known as a PIR motion sensor. A PIR motion sensor is a little less accurate. It won't tell you how far away something is when it moves. It only gives you 1 bit of information, and that corresponds to the answer to the question, has something moved around me or not? However, it's much easier to use with the rest of the system and only requires 1 GPIO bit. This over here, this line that needs to interface with the ADC isn't quite correct. You can use a PIR, to my knowledge, with an ADC, but we ended up not doing so. And we tuned the sensitivity with the two dials underneath this board to allow for the best interfacing with our environment. Now let's discuss the software architecture. We wanted to program this at a fairly high level because it's pretty difficult to, again, work in a register-based environment. So we used open source code, both from Texas Instruments in their demonstration of how to interface with the 74HC595 shift register, and my roommate Kevin Lin's LCD device driver to interface between the peripherals and the MSP430 from a high level. Our system is implemented as a polling system where we have certain variables that keep track of state, like which song you're at or what is the most recent reading of the PIR. And depending on the input values at each poll iteration, we decide to do something, right? So if we notice that the switch button has been grounded, we trigger the current song to be played. We shift, or we clear the LCD and display the new current song's information, and we do a delay cycles to allow for the switch to debounce and identify the next song to play. And the same thing happens if we notice that the PIR has just gone high recently. Otherwise, nothing happens, and you'll stay triggering the same song until you decide to switch. There are several room for improvement for this particular system. One that comes to mind immediately is for an interrupt organization rather than a polling organization. We didn't have quite enough time to reorganize our code given the constraints for submitting our assignment, but it definitely wouldn't be too hard to do, and it would be pretty good about saving more power when dealing with the actual system. However, it's not going to save that much more power, because note that the soundboard itself and the speaker do run with a substantial amount of current flowing through, and since current is proportional to the power lost by a system, then chances are going to sleep with the MSP430 isn't going to save like a lot of power in the grand scheme of things. That's just something to think about. Yeah. So what kind of concepts did we utilize in making this project? Well, we looked into several of these kinds of different categories, and in the end, the main three components that we ended up doing were, and they're not entirely listed here, but they were how to interface with lower level devices, right? Like LCD screens or flight sensors and stuff like that. How to port code that you have found from other libraries and for other programming languages and other devices into something that you can use for your current hardware setup. And also things like soldering, breadboarding, PCB design, sensor inputs. We looked a little bit into ADC utilization, but figured that we didn't have enough pins to make it possible, and it seemed pretty hard to do in conjunction with a PIR gesture or PIR sensor, but we did look into it and learn a little bit about it. The next steps would be implementing our system design on our PCB. Since we were pretty limited on time, we did design a PCB for the project, but we didn't end up using it in context of our final deliverables because we ended up switching the design thanks to difficulties with things like the I2C and like some minor traces being rerouted. If we had a little more time, we would update our design to reflect our current schematic, which is the one I showed earlier, and we would reorganize the software to use an interrupt-enabled system instead of a polling system. We could also use a more sophisticated motion sensor, like the flight sensor, and add different capabilities to the radio station depending on what kind of value is read. For example, if you're 30 centimeters away when you move your hand, it'll skip by one song, but if you're 15 centimeters away, it can skip by 2 songs, or something similar. We probably do need a little more work in dealing with direct communications, like I2C and SPI protocols. We did get successful serial communication in this project in talking to the shift register, but again, we did not succeed in dealing with I2C, so that is a room for improvement in the future. And the upgrading of the soundboard, of course, could always lead to potential improvement in the quality of the audio. And one thing that isn't mentioned here that I'd like to mention is that the daisy chaining of the shift registers could allow for a lot more control than in our initial and current design for the board. And that's about it. Thanks for listening to my presentation, and I hope you have a wonderful day.